Now I got to figure out how to hold a microphone and the pointer all at once. Mick Jagger probably has this trouble too, right? Well, thanks for that introduction there, Bill. I think I've talked to you several times before over the years as a botanist studying rare plants. I got my degree in botany in Wisconsin and came out here in 1993 to study rare plants. And now suddenly I find myself studying fog as well. And some of you have asked me why, and I kind of wonder why. Why am I doing this? Why am I studying fog when I really am a botanist and I don't know much about fog? Well, I have to tell you a little bit of a testimonial here. When I first came to Channel Islands, I climbed up on the tower that's out here and I looked out over the ocean and I looked for the islands and they weren't there. They weren't, it looked just like that. They weren't there. So I went up the next day and I looked and they weren't there. And I looked for a week and they weren't there. And finally I went to Kate Faulkner and said, you know, I came here to work on some islands. Are there really islands in this place? And she goes, oh yeah, they're there. So after 30 days, I finally got to see the islands and I was not convinced that I had made a total mistake in coming out here from Wisconsin. Once I got to the islands though, I had some more trouble. I had a map, but I couldn't see anything. I couldn't find my study sites because it was so foggy. I'm driving around. Where's the study site? Oh, there it is. I think that's it. Yep, that's it right there. So I get out and I'm doing work and I'm soaking wet in 15 minutes. My data sheet's wet. The pencil's tearing through the paper. And I'm asking myself, why? Why am I doing this? And this is why. Let's see if I can run this thing here. Oops. Oops. So I need to just click on it.
Click.
Wow.
Click on the arrow.
I'm trying to do this with my left hand. Hold on, let me get this with my right hand. Yeah. This is what's happening on Santa Cruz Island. This is a video taken by Sarah Baguskas, who's studying fog out there on Santa Cruz. You can see that the fog is just pouring over the ridge. She's standing on the ridge road up high on the top of the island. The fog's pouring over to the north. But look what happens. As you look to the south, it's also pouring off to the south. You can see it draining off the other direction too. So the fog's coming over this hill here, hitting the ridge and just cascading down the island. And if you happen to be right there trying to fill out your data sheet, guess what? You're going to get pretty dadgum wet. So this can happen almost any day. Anytime you go out to one of our northern islands especially, you can encounter fog like this. It can come up pretty quickly and be very surprising. In fact, it's not at all unusual to climb up onto the pier at Santa Rosa and get off the boat, climb up, see some of your colleagues and friends and go, hey, how's it going? And they were like, great, it hadn't been foggy. Matter of fact, it's been quite beautiful. And you know, I think from this kind of attitude, fog has gotten kind of a bad rap. You know, it's miserable to work in sometimes. Richard Wagner, all the way up through Alfred Hitchcock in Psycho, have given fog a bad rap. But I've actually come to think it's actually quite beautiful. And if you came a little bit early, you saw some slides that colleagues and friends of mine have taken, just pictures of fog wherever they go on the islands. And it really is quite pretty. So I have come kind of reluctantly to this in my later years as a plant ecologist here on the islands, and I really have come to have a fairly profound appreciation for fog, and I hope that after tonight you might change your attitude about fog too, if it was like mine. So one of the first things I want to tell you about is I think that fog is a very strong ecosystem driver on the Channel Islands. And by driver, I mean something that affects entities in the system like trees, bushes, vegetation, but also processes like how water moves through the system. I didn't study fog to begin with. I studied other things like plants and lichens. And one of the clues to why I think it's an ecosystem driver is the presence on these islands of fog-loving lichens like this one, the lace lichen, which exists only where fog is. It's a fog indicator. And you'll find it on the islands. You find it also on the nearby mainland. My field of study has been rare plants, and we have a lot of endemic plants that turn out to be fog endemics on the island. They live only in places where there's reliable fog, like, for example, in this area, here's a canyon where the fog pours over. So in canyons that are exposed to foggy areas, bluffs where you might expect there to be fog, like this bluff on San Miguel, and even bluffs that are sticking up in the interior of the islands, but into the fog zone and intercepting fog. So I started looking at the distributions of these plants, saying, wait a minute now, fog is somehow driving where they are. Another species that really is a fog endemic plant is the Torrey pine out on Santa Rosa Island. It's been studied as the subject of Park Williams' dissertation a few years ago. I think he published his dissertation work in 2009, 2010. And he looked at the Torrey pines and looked at growth as it relates to fog. So pines grow more in rainy years, that's good, we kind of expect that, but they grow even more in foggy years. And what he's done here is look at, look at bands of growth. So here was a fairly wet year, a fairly wet year, a fairly wet year, a couple of dry years. And so this R squared value here means a lot to a scientist. That means the strength of the correlation of growth to rain or growth to fog. And you can see that there's a very high R squared related to fog here, and a pretty high one related to rain. So water profoundly affects how plants grow. We all know that, right? But fog is a real big driver of how fast and how much and when the Torrey pines grow. Another thing that you see out on the islands is something that I learned about as a botanist in the desert, this phenomenon of nurse plants, where there's a plant that somehow facilitates or nurtures the advent of another plant in the system. In the desert, usually the nurse plants are just providing some shade, like a big cactus that can let a little plant grow beneath it. On the islands, these scrawny bushes, whoops, these scrawny coyote brush bushes are actually facilitating the germination and growth of this island oak, which could potentially be a 300, 400, 500-year-old oak, big majestic plant. The oak would not be there if the coyote brush were not there. The coyote brush is providing shade, but more importantly, it's collecting fog drip that's delivering water to the ground so that that oak can grow. I don't know if you know much about oaks, but if an oak acorn dries out, it won't germinate, it'll die. The embryo inside will die, so it has to have moisture. It can't survive in places where there is not enough moisture to keep it wet from the time it falls from the tree to when it germinates. And that's what's going on here. Another clue for me, the naive botanist, about fog in the system. The bishop pines are another fog endemic plant. They have a much more widespread distribution than the Torrey pines. They grow all up and down the coast. In fact, during the paleoclimate time, when it was very cool, they grew far inland. But now they hug the coast wherever there's fog, and they're out on our islands as well. And this is what it looks like in a bishop, or what it feels like in a bishop pine grove when there's a fog event. This is a summer day. It's probably 90, 100 degrees in Ojai where I live. It's probably in the 90s down in the Central Valley at the main ranch of Santa Cruz. But up on the ridge, it's raining. It's raining in the pine trees. This is very close to the study site where Chris Still and his students, Park Williams, Doug Fisher, and Sarah Boguskas, have been working since 2004, and they've been characterizing what happens with bishop pines in the fog. Also, one of his students, Mariah Carboni, has looked at carbon cycling in fog. Pretty incredible. That's a lot of water. What has been happening lately, though, you've heard about climate change and how it's coming, but actually climate change is here, and it's been here for quite a while. And one thing that Chris and his students have found is that the fog pattern of distribution is changing on Santa Cruz Island, and it's probably changing elsewhere as well. It's moving back, it comes up into this bishop pine grove from the Christie Ranch area, and it's moving back toward the ranch. As it moves out, you see death in these trees here. And so these dead trees are there because the fog is moving away. And Sarah is trying to figure out, Sarah Boguskas is trying to figure out, does that affect young plants, old plants, all pines? And she's finding it actually affects the older plants disproportionately more than the younger plants. And so we're losing the distribution of the bishop pines on the island because the fog is changing, because climate is changing. Another really amazing thing happened. Kerry Knutson is a lichenologist who went out to Santa Cruz Island, and he found some species of lichens that only grow on tree bark. Bark of oaks, big majestic island oaks, small scrub oaks, and chamise. the oaks are nowhere around here. The oaks are gone, and here are these oak lichens growing on a rock wall. This rock wall is high up on the ridge of the island, and these oak lichens have found this rock wall to cling to while they wait for their ecosystem to come back, or their oaks to come back. This is kind of important to me for a couple of reasons. One, it shows that there were oaks around there. They were there. The lichens are there. And there's enough moisture up there to sustain these lichens, and most likely also a lot of other plants and algae and things like that. So I walk around the landscape and I look at it and I think, wow, the oaks are missing. What else is missing? I mean, you know, we're getting all these clues that things are not as they were. It's a beautiful landscape, but it's missing some things, and what it's missing profoundly are shrubs, scrub, chaparral, bushes, whatever you want to call them, covering the hills. This is a place on Santa Cruz Island near China Harbor where the scrub is recovering. And if you think about it, this is what the Conejo Grade looks like, what the hills behind Ojai look like. They're scrub-covered hills. The islands used to be like that. They're not like that mostly anymore because the grazing animals ate the shrubs, trampled the shrubs. Erosion then came in, washed the soil away, washed down the bedrock, and profoundly changed the system. The other thing that really is important to realize here that I didn't realize for a while is that the scrub supports stands of these emergent trees. And I'm telling you that the oaks need the baccharis, the coyote brush, in order to grow, in order to have a seed bed that's moist enough to live and grow. If you don't have that scrub, you won't get the oaks that dominate, or used to dominate the ridgelines and do in some places still stick up out of the chaparral. So we botanists call this emergent woodland. It wouldn't be there if the scrub weren't there to begin with. And so the scrub is kind of like a nurse community that then nurtures these big plants. And when you look at these big tall trees, you think, wow, you know, they should get some bushes and plant them under here. Really, what we don't really think of carefully is the fact that you've got to have the shrubs first before you can get the trees. It's not a simple matter of just getting trees out there. When we walk around Santa Rosa Island, we see the shadow or the ghost of chaparral past. And what you're seeing here is a map that Sarah Cheney and others put together that shows where we see little remnants coming up that are chaparral plants. This whole green area, when we walk around, now, especially now that the deer are gone, we are starting to see little sprouts of chaparral plants like toyon, chamise, scrub oak, mimulus, gypsonia, some of the things that live in the chaparral. Matter of fact, when you look at some of these plants, you look at the base of them and they have a burl that's 6 to 10 inches in diameter at the base. They've been living there for hundreds of years, somehow persisting all those years of grazing, coming up, putting up some leaves, getting them grazed off, put up some more, getting them grazed off. They've got incredible root reserves and they're coming up. And that's how we have come to draw this chaparral shadow. Right now, where the purple is where we see chaparral, and where the blue is, we see emergent island oak stands. So this is traces in another clue to the what's been going on in the past, where the oaks might have gone, where they might have been, and where they could be in the future. So this is what Santa Rosa looks like currently in some of the on the high ridge. It's beautiful and all that, but to me, when I see it, I feel very sad. This is what it could become, or what it has been. And so I came to this sort of what to me is a staggering realization, and I say that candidly. I mean, I really was not thinking about this with my eyes open for about a decade or so, that what we see on the landscape out on Santa Rosa and a lot of the other islands, and also on the near shore mainland, is not how it used to be, and it's so different, it's hard to imagine how it used to be. And in ecosystem science, we think about systems and how they function and how sometimes they can go over a threshold into an abyss that they can't get out of. And this is a system, I am sure, that has gone over a threshold that is related to having lost all of its vegetation and therefore having lost a lot of its function. We hope that it's not in the abyss. It's definitely got a lot of advantages over its mainland counterpart because it's in the Park Service. The Park Service has gotten the grazing animals off and is dedicated to conservation and restoration. You don't get that chance almost anywhere else in the world right now, especially in a Mediterranean climate. So I have become convinced that fog is a driver, and these are some of the reasons. It determines in large effect which species are there, like these lichens or some of these fog endemics. where they live, like the small annual plants on up to the trees, where they are on the islands. How fast they grow, like the Torrey pine that grows more in fog years than not fog years. Whether or not they can germinate, is there enough moisture for them to come up? And when they die. The bishop pines are dying because of the lack of fog in some places. So that's all great and good, and so, you know, my science brain goes, okay, oh, so it's out there, it's drifting around, what's it really doing? You know, I can see what it's not doing, but what is it doing? And I have had great fun working with Sarah Cheney, who many of you know. She's kind of like the artiste restorationist. She can grow anything out of anything. And she's kind of got the vision about how things used to be and how they could be, and I'm still standing there going, yeah, but what's it doing? So I went off on a science tangent here, got a little bit of funding from the Park Service and more funding from the USGS to give it a go and see if we could describe what's going on in the system. So where is the fog? Well, like most of you probably know, it's all up and down the coast, in Southern California on up into Northern California, very close to the coast. It's also out on our islands. It's swirling around constantly out there. This is a satellite image. A graduate student in Chris Still's lab, who's just now finishing up his master's degree, named Bharat Rastogi, is working with GOES and GOES satellite imagery and other imagery to figure out what is the pattern of fog inundation on the Channel Islands. I asked him to work particularly on Santa Rosa, but he's been including the northern islands and is expanding his work to the southern islands as well, so keep an eye out for his information. Basically, he's been using geostationary satellite data that passes over our area at least twice a day. He's gotten the images twice a day for 3 years and has characterized when the islands are covered with fog by this process that he outlines here. It actually is just a common sense process, but it takes a long time to work all this out. Basically, he figures out when the islands are covered with clouds, when the clouds are sufficient and sufficiently dense enough to be fog, and then he takes the overcast data from the Santa Barbara airport and says, where is the base of the fog? I'm going to project that out to Santa Cruz Island and Santa Rosa Island, San Miguel, and I'm going to see when the cloud is actually in contact with the ground. And so a cloud in contact with the ground is fog. A cloud above the ground is a cloud. It's overcast. And both of those things turn out to be very important, so don't forget the overcast. What he's found is that fog inundation follows an elevational gradient as you go across the islands. The wind comes predominantly from the northwest, sweeps across here, and as the wind comes across the ocean, it picks up moisture, encounters the terrain, and goes up in elevation to this high ridge that it runs across Santa Rosa Island like this. There's a similar ridge running across Santa Cruz Island. This ridge on Santa Rosa is almost perpendicular to the wind flow, and so it's a great fog capturing device. And you can see the darker green is the more intense fog, and it's more foggy here in the high places. The other thing that happens is once the wind comes in here, rises up and cools off and squeezes out its moisture, you get a rain shadow effect on the other side of the island, especially in some places. There's certain canyons where the fog can still spill down, like we saw in the picture from Sarah Boguskas. Certain places that doesn't happen. So this gives me, a botanist, a clue as to where I might find things growing well in the fog versus not very well. This is a pattern that he put together showing how the fog lays down and what the spatial pattern of fog is across all of the islands. So you know, this is San Miguel, Santa Rosa, Santa Cruz, and Anacapa. He finds that July is about the peak time for fog. September it starts to peter out. But no matter what time of year it is, there's more fog out here on San Miguel than there is on Anacapa. You probably didn't need a fancy model to figure that out. Everybody who drives a boat knows that. Anybody who's been to San Miguel knows that. But it's kind of cool that he can detect that using these methods, so that now we feel pretty confident that these methods are ones that we can use in other ways to get at fog distribution. You'll notice here the scale bars are different. So the red is intense fog to less intense. In September, the intense fog is not that intense, but his purpose here is to show you that no matter what time of year it is, this is the pattern. If you're interested in the pattern and how things change through the year, what Bharat has found is that fog really sets in May, intensifies through June, peaks in July, late July and August, and then begins to subside again in September. So that coincides with the hot months, and what's driving this is the inland heat is in the desert in Ojai, where I live, is rising up and pulling air behind it as it rises off of the ocean. And it's a fog machine. It's just pulling air in constantly. And this is especially pronounced in the May through September summer months. We live in a Mediterranean climate, which is great for our economy in some ways, tourism and all that. This is what happens in a Mediterranean climate from a plant's perspective. And let me tell you a little bit about this, because it's important and it's kind of fascinating to me. What we have here is a compilation of data from Chris Still and Doug Fisher, who've been working out on Santa Cruz in those bishop pines. And what they're showing here is what is going on with water in the bishop pines. And you could generalize this to the Torrey pines, island oaks, other plants in our systems in the Mediterranean areas of the world. Basically, here's rain. The rain comes mostly in Spain? No. It comes mostly in the winter months. Actually starts out, next month, October, November, peaks in the winter, and then declines to almost nothing in the midsummer. We all know that, right? So, like you would expect, soil moisture kind of follows that pattern. The soil takes a little while to get wet, but once it's been raining a while, it gets wet, and then as the rain quits, it dries down. Runoff is a constant part of the system. Runoff is pretty low in the pines where they've been working because it's pretty well vegetated and there's a lot of litter on the ground. But what is interesting here is this line, this orange one, the PET, is the potential evapotranspiration. This is the demand that the climate is putting on the plants for moisture. This is the demand that the plants need in order to keep growing. This is what is going to shut down growth here, because the red line is the available moisture. And so you can see that after about March, when the rain starts to decline, there's a deficit, a moisture deficit that builds up in the system. Lucky for us, the fog is there to rescue the system. It peaks in those months when the rain is not there. And so, remember I told you about clouds? We've got both clouds and fog in the system at a time when the system needs it the most. Here's what's going on in the middle of that deficit in an island oak grove on Santa Rosa Island. Kate Faulkner made this video a few years ago. That's wind. Wind is always there too. And that's not your neighbor's sprinkler system, that's rain inside the grove. If you just take 2 giant steps and go outside the edge of the canopy, it's dry as a bone. You're not getting wet. You don't need to put your hood of your jacket up. You don't need an umbrella. You don't have that kind of rain. It's phenomenal. It's really striking how much water comes in these groves. So what's it doing? What's the fog doing? Well, it's dripping and shading. So the clouds are shading. The fog is dripping. And if any kind of luck, the groundwater is getting, the root zone and the groundwater is getting some water from the fog. Well, that was the Cliff Notes version. Here's the Geek Model, the science model. I got a bunch of scientists together and we went out to Santa Rosa and walked around, and then we sat down and drew out, using all of our collective expertise, what we really think should be happening, should be the way fog functions in the island system. And you could generalize this to the coastal areas of Southern California, anywhere in the fog belt. So what we need to pay attention to here are the arrows and what's going on. So we have cloud cover, and this F season means depending on the season, it's a function of the season. Sometimes it rains. Sometimes we get fog that blows across, intercepts the canopy, and drips out. And there are a lot of things that affect that. Well, it drips out. Where does it go? It can go down the slope on top, causing erosion. It can go into the soil a little bit of a ways, and then through the soil, and come out in a seep or in a stream. It can go all the way down to bedrock, to a water table, and get into the ground flow and sustain what we call base flow in streams. A lot of our streams in Southern California depend on periodic seasonal moisture. Where that moisture is going is into the bedrock and into the groundwater, and it's being kept there and eked out slowly over the rest of the year as what hydrologists call base flow. On Santa Cruz Island and Santa Rosa Island, I'm told by old-timers that there used to be base flow in some of the streams. And maybe the archaeologists will have some more information about this too. But the streams are dry now. And I think one reason is because this system is broken and the base flow is not getting in as much as it should. The other thing that's happening is that evaporation is happening off the surface, and trees are transpiring, so trees give off moisture through their leaves. And so we have this kind of circle of relationships between the fog, the clouds, and the trees and the soil. And that's why we call it an ecosystem process, because we're actually looking not just at one entity like rare plants or a tree. We're looking at how does moisture move into the system, move through the system into the soil, and affect stuff far downstream like base flow or even sedimentation in the marine areas. Well, so part of our science question is how much fog is there on Santa Rosa Island. We've chosen to look just at Santa Rosa Island sort of as a microcosm that we can handle here. We've set up 5 weather stations dispersed around the island in places that Barat's map told us we should be finding some differences in fog. And we have also put some what we're calling fog throughfall collectors in the Black Mountain area. And I'll tell you a little bit about how that's all working. Our 5 weather stations, what we're doing there is we have regular, what I call normal weather data, wind, speed and direction, relative humidity, solar insolation, precipitation, and we've added this really cool device here that Chris Still and his students worked out. It's also collecting fog. It's giving us an indicator of how much fog is in the system. We're also interested in, remember how the fog comes in, intercepts the tree canopy and drips down? Well, are all tree canopies the same, or are some better at harvesting fog than others? And so we've got collectors under 4 different species of trees. This is in a Bishop Pine Grove on Black Mountain. And what's happening is, here's the rain gauge down here. We've got a funnel upside down on top with some high-tech plastic on top. And we have these troughs, and the water is dripping through the trees into these troughs and going into the funnel, so we can measure what's coming as fog, but not what's coming as rain into the top of the tipping bucket. We call these things fog harps. This is not a scientific term, so don't say it to all your friends. But when you stand next to a fog harp, when it's blowing about 30 knots, and it's cold and it's windy and it's soaking wet, you can see that these filaments are collecting water. They're sticking up in the air, they're acting like leaves. Drops of water are collecting on them and falling down into this trough that then feeds into the tipping bucket, the precip gauge down here. I don't know if you can see that very well, but there are drops coming off here and going into the bucket. And it makes quite a noise sometimes when you're standing right next to it. So this is what we're finding in the data from those stations. This is fog drip for the full year, pretty much the full rain year of early or late September 2011 to September. I threw some December data in there from 2012. So what we're seeing is that there is a lot of moisture. This is millimeters of water, which is how meteorologists measure rainfall. They measure it in millimeters. We're seeing that, we're corroborating Barat's model here. We're saying, he's right. This high elevation site at Hoya Vieja up on the high ridge at 432 meters, that's about 1,400 feet, one of the highest places on Santa Rosa Island, is really collecting a lot of fog. You can see we had some voodoo stuff going on here. We lost a bunch of data. That's why there's that gap. That's how it is when you're taking care of remote weather stations, I guess. And I apologize for that, but that's how it is. But anyway, you can see that the fog is there. You have events. It'll come in 5 or 6 day fog events that are driven by these subtropical and tropical cyclones that push fog up this way. But the progression of fog is constantly there, and it really picks up in the late summer or midsummer onwards. So this is the cumulative total of what we've had at those sites, and you can see that basically the elevation gradient that Barat found with his model is holding true in our data collection. I've taken these sites and exploded them a little bit bigger on the next slide so as you can see what's going on there. So the Arlington site and the Sierra Pablo site, the red and the blue, are at about the same elevation. Arlington is on the north side, Arlington and South Point are about the same elevation. Arlington is on the north side, South Point is on the south side. And so you can see the effect not only of just fog, but also being on the north side, on the windward side or the wet side of the island. The same kind of holds true for the Torrey Pines and the Sierra Pablo site. The Torrey Pines is in a northerly location. The Sierra Pablo site is down here on the other side in that rain shadow. So we're seeing very strong patterns with elevation and also with where on the island it is with respect to which direction the wind comes from, north or south. Whether you're on the north side of that ridge collecting rain or you're in the rain shadow on the south side. By contrast, here's the rain we measured right next to the fog harp at the same site. I put this little circle here so that to remind me to tell you that this is 250 millimeters here. That's as good as the rain gets at our sites here. So you're looking at really very little rain compared to how much fog is being collected on those sites. Now, what we're trying to do with these fog harps is just get an idea of how much fog there is, and if we ever wanted to use the fog, like they do in South America, Latin America, as a water source for drinking, for watering animals, for growing plants, could we actually collect a lot of fog? And if we could, where would it be good to do that? And is this a good thing to use, this kind of monofilament line or something like that? So what I'm thinking here is yeah, it's a good thing. We get fog, we get a lot of fog, we get fog at high elevations, we get fog when the rain is not raining, and all of that is very important. Here's just a kind of a snapshot of what's been going on with the throughfall. I tell you, we're collecting water that's dripping through the canopies. We're not measuring them on equal footing, so it's not really fair to compare this fog that was collected with the fog harp to fog that was collected in the throughfall. The throughfall troughs are very small in area compared to the harp. But basically, when it's foggy at Hoya Vieja or at Soledad or at Black Mountain, it's dripping through the trees and it's getting to the ground, and the trees are also intercepting some of the moisture, and the trees actually absorb moisture through their leaves, and so this is a good thing for the trees. If you then want to compare species to species, here's throughfall in the island oak at Black Mountain. Here's how island oak compares to scrub oak, bishop pine, and coyote brush. I thought island oak would be the best harvester of fog, but it turns out that bishop pine looks like it is. Coyote brush, pretty substantial, not bad for a plant that maybe is knee-high, thigh-high, something like that most of the time. And so to kind of put this on equal footing, like how much is that? Here, this bar at Hoya Vieja, over the 40 days of rain of fog drip that we had here, collected 22 gallons. That's about half a gallon a day. And to put it kind of like some way that equates to my husband's understanding, that's 4.5 beers a day. That's not a lot. You could just go up there and sit there and drink, or not drink beer, but dump beer out, and you'd have that same effect. So there's a lot of moisture coming through that's captured by these fog harps and potentially by these trees. So then the question is, well, okay, great, it's really foggy, but where is it going? Is it going in the ground or what? So I invited a bunch of USGS colleagues, scientists. These are all scientists. These are not guys out on a picnic. They're staring at a soil pit here, contemplating the gravity of the situation. What we're doing is we are now monumenting and trying to understand the total water balance of this oak grove. We call it the Soledad Oak because it's at the top of the Soledad drainage on almost the highest point of the island. The Soledad drainage is one of the biggest watersheds on the island, and it drains out to the south. It's a fairly small stand. It has right now about 16 trunks, but older photos show that it had way more than that. And this little slot you can see here, actually there were trees in the 1980s down here as well. So it's an oak grove in trouble. There's no regeneration going on around it. We want to know what the water balance is so that we can understand it and we can fix it if possible. So what we've done is dig these soil pits. We have 3 of them. There's one here, right under the canopy of the oak. There's one here about 2 meters outside of the canopy, just outside of the drip line. And there's one over here about 20 meters out from the canopy. We want to see what's going on under the oak canopy and next to the oak canopy. We also found a seep coming out of the ground. See if I can do this without, there's a seep right here. So we have a pressure gauge that's wired into that seep so we can see is there water coming out, and if so, when. And then here's John Stock, a USGS hydrologist, he's putting in a flume with an infrared sensor on top of it. It's going to tell us when it rains or fogs or whatever, and water's coming down this water catchment area, how much is going off the top. We also have these things we call little Mars rover dudes, also not a scientific term. These are devices that are sitting on the ground with another infrared sensor that's looking at what's going on right under it. So when it rains or when we have fog, it's telling us how much sediment is passing through underneath it. So we're getting an idea of what's going into the ground and what's running off. What's running off is sheet flow on the surface and what's gushing down these gullies. So our soil pits have 3 sensors in them at 5 centimeters, 15 centimeters, and 25 centimeters. One of the questions for a botanist is, where is the water? Is it in the ground? And if so, how deep is it? Is it deep enough for a plant to actually get to? And does it evaporate fast? And so they're helping us figure that out. And so this is what we see in that pit that I just showed you a picture of. The pit is covered up now. It's not a hole in the ground like what I just showed you. It's covered with soil and litter, and it's looking like just part of the ground. So here's what we see. This is the rainfall that we have been measuring with a precipitation gauge at that site. In September, we had to get it really wet in order to charge the probes, and then we've been watching it since then. This blue line is the water, is the soil moisture at 5 centimeters, so very close to the surface. That's about this close to the surface, well within the rooting zone of annual plants. The 10 centimeters down and then 25 centimeters down. And what you can see basically through this picture is that there's consistently more water deeper down under the tree canopy in that soil pit. There, between 5 and 10 centimeters, as it rains, the water in the soil goes up, but it declines, and it goes up, and it declines. And so it's responding very quickly to rainfall, but it's declining more rapidly on the surface than it is at depth. And the really cool thing about this that my geologist colleagues actually got excited about was the botanical part, which is it stopped raining. Our last big rain event in 2012 was in mid-March. All of this now is fog water that is actually drizzling into the precip gauge. And so under the tree canopy, where water is falling, the tree canopy is intercepting water, it's shading the ground, the fog is shading the ground as well, and the moisture is staying pretty high in there. What about if you go farther away from the tree canopy? This is looking at it a little bit different way. So here again we see at 5 centimeters that blue line that you just saw on the surface. If you go right next to the tree canopy, you have this orange line, and then further away, the 20 meters away is this one. And we see the same thing. The water's going up and down with the rain. It rains, the water goes up. The intervals between rainfall, the water goes down. But it's vacillating like crazy toward the surface. And it's vacillating like crazy far away from the tree. So if you're a plant that needs to have reliable water for a few days, you can't dry out, it's not going to be very good for you, whoops, out here 2 meters away or 20 meters away from the tree canopy. So if I were trying to grow an oak, I wouldn't plant an oak out there, I'd plant it under the canopy. Same thing, just deeper. What you can see here is the same pattern. Basically, under the canopy, the water is more consistent. Away from the canopy, it's going up and down. After the last rain, it tends to go down and stay down. What's going on at that seep? The seep is responding to rain as well, and basically what we're seeing here, without going into great detail about it, is that it rains, and then about a day later, the seep seeps out a little water. It flows. So there is some water going into the ground and coming out through that seep, which is pretty cool. But basically, if we go back to our model, what we've been trying to characterize is the strength or the size of these arrows so that we can fill in some of these function of things with equations saying how much water that equates to. And what we're seeing is a system like this or somewhat like this where instead of a lot of water running off underground, a little bit is, and more is running off the top and not much is getting into recharge. And so you take the vegetation out and you have a different picture. So we need vegetation and we need fog. And you know, my clues as a botanist, I think, are corroborated by some of the data we're seeing right now. So what does that bring us to? Restoration. This is where Sarah Cheney really kind comes in, and she's been instrumental in helping us collect this data as well. But we've got a grant now starting next year for 3 years to do some restoration work. We're going to restore the upland chaparral. No problem, right? This is a Google map photo. Here's northwest. Here's that ridge that cuts across the island. It's up in the fog, wet. And you can see that it's lacking soil, and we have some remnant emergent vegetation, which indicates that there was scrub there, and there is hope for the future because there's something there still. So we went through this structured process, a decision-making system called the Restoration Rapid Assessment. Ken Neeson, who's sitting over here, was one of the people who did that. And we went to the field, Ken and Sarah and Ron Hebert, a Park Service guy, and looked carefully at every site that Sarah thought should be restored, particularly in addressing sites that Barat's model and our data showed may have the potential to collect fog, so that we could use fog as a restoration tool. This process makes you be very careful about what you say and how you say it, and communicate very clearly what you think about the site. For example, what's its value to the park managers, to people who are writing the general management plan? And some of these sites came up very high on a scale of 0 to 100 because they have, they're up on the peak of the island where everybody can see them. They have island oaks, or they had island oaks, so they have a lot of value to managers. We also expressed what we think the natural condition of that site was like. It had vegetation on it. How far is it from that condition, and how long, what's it going to take to get back to that natural condition? And realizing that we probably never can, with the kind of funding and our lifespans available to us, get back to that. What's a reasonable management goal? And what's it going to take to get back to that goal? So the system, while it was kind of difficult to implement because you had to think really hard, sitting up there in the fog and wind, not drinking all that beer, it really did make us be very explicit about why we think the sites have the capacity they have or don't. And from this, we've been able to choose about a dozen sites that we are going to focus on in our restoration project. And you can see that they vary from almost as good as it gets in a Highland Oak Ridge situation like this at Black Mountain, to almost as bad as it gets like this on the Soledad Ridge in what we're now calling the Hoya Vieja Oaks, because they're draining into the Hoya Vieja drainage on the south side of the island, or the north side of the island. Yeah, we've had a lot of confusion about that over the years. So one of the major things we need to do is erosion control, and Sarah Cheney actually had some funding to try out some techniques back in 2005, and they met with great success, except that the elk tore them up, and so there's not much of this left. And so we learned a lot from what she did about how to control erosion, how to catch water, litter, soil, and seed. And I think maybe some of you probably helped her with that project. I know you did, Ken, and some of you are nodding your heads. So this is what we're going to do again with more funding and no animals to come and mess it up. We're going to be collecting seed. We actually have started collecting seed of plants that we think could grow up there, would be part of that chaparral, but more importantly also native plants that exist there that can grow in those conditions, and ones that can sustain the conditions up there. We intend to use fog harvesting structures like these that are used on Catalina by some of our, San Clemente, I'm sorry, some of our colleagues out there. Screens that catch water and drip them onto their plantings. We need to make these smaller on Rosa because the ones that we tried blew over within about a couple of hours. But you know, if you fence a little oak tree to keep the deer and elk from eating it, you actually have been watering it as well with the fencing structure. And so we'll be doing some of that kind of work as well. We'll be using the fog and structures to help us water the plants that we put out there, either as seeds or as plants grown in the nursery. And then the other thing that is really the cool thing about the Channel Islands is that we still have remnants of plants that are out there that actually harvest water and are nurse plants for other plants to grow. And here you see some of those, whoops, little tiny, just newly emerging stipa grass, needle grass. You wouldn't think would harvest much water, but look what those did in one night. Here along the road, you can see baccharis, individual shrubs dripping water onto the ground. Here's even an annual brome grass that provided enough water for this island plant to grow. And then here's a picture of an island oak coming up in coyote brush scrub again. So we want to use these plants in our restoration, and we're using these kinds of places on the island as a model. Here you can see this denuded, barren island oak grove. Here is a place where So I planted a little bit of stipa grass and it took hold and it's growing, and you can see it's stabilizing the ground here, and it's providing the soil conditions and the opportunity for other plants to come in. Likewise, this, when I first showed up here, was a barren slope. When the cattle were reduced and the deer and elk culled back to low numbers, the stipa grass started coming in like this, and then the coyote brush started growing, and now we're seeing small island oaks growing in that nurse plant effect. Also, since the deer have been gone and the browsing on the native single island endemic endangered Arctostaphylos manzanita is able to grow, we're seeing it growing under the drip line, right at the edge where the torrey pines are dripping water down. So these are our models that are out there on the system that we're looking at to say, you know, we could use these plants, we could use that fog to our advantage for a restoration project. So instead of saying, you know, why fog in a sort of a despairing way, I've come full circle to having a pretty good appreciation for what fog does for us as an ecosystem driver, and it's because I'm a scientist and I've collected data and I believe the data. And I'm delighted to be working with Sarah on some restoration projects now, and hopefully some of you will join us on that. So my motto for this project is put the fog back in the East ecosystem and we'll get the ecosystem back. Thanks a bunch for coming, and I hope that you can come out and help us. Yeah, sure. We've got time for some questions, and I'm supposed to repeat them. Yeah.
If you were to measure in inches, not millimeters or centimeters, what would be the average rainfall of equivalent of the fog on Santa Rosa per year?
Well, you know, let's see, it's 0.2 millimeters is intercept, or 0.82 inches is 0.2 millimeters in those buckets, so about 4 times as much in inches as in millimeters. So the average rainfall is about 10 inches. It's the other way around, yeah. Yeah.
The average rain, and how much is the average rainfall?
The average
rainfall.
The average rainfall over the years is about, if you average over about 30 years, is about 10 inches per year. And the fog looks like it's about 4 times that amount if you average over the 3 years that we've been collecting fog data.
Great, that's a wonderful way
Yeah,
to visualize.
Yeah, I should do that. Next time I'll put the inches on there as well. I've been thinking in millimeters for so long.
Yeah, maybe we'll get there someday.
Yeah, other questions? Yeah.
I was wondering if fog is as important in other ecosystems that aren't Mediterranean ecosystems, like the Pacific Northwest, where there is more rain, but there is also a lot of fog.
Yeah, the question is fog also important in other systems? And I think most definitely yes. I think it's proportionally more important here in our Mediterranean system because it's coming at a time when the rain is not coming. But certainly in the Pacific Northwest, you wouldn't have those enormous trees, you know, the Douglas fir forests, the spruce forests. You wouldn't have the redwoods if it weren't for the fog, even though they still are getting a lot of rain. So yeah, I think fog is all over the place, but I think it's especially important here in our system. Yep. Go ahead.
She was asking about the redwood. If you get into the northern redwoods, if you look at the coastal redwoods, they only grow in the fog belt. And if the fog belt moves, they start to die.
Yeah, the comment is that the redwoods are growing in the fog belt, and if the fog moves, they start to die. And that's exactly what's happening. Bharat is going on to do his PhD work, and he's working with redwoods, and that's what he's finding right now is this model of fog inundation, going back and looking at old satellite data, is showing that the fog is moving, and the redwoods are stressed because of it. Yeah. Ken, you had a question.
Yeah, the restoration plan is taking into account climate change and how the fog is going to decrease on Santa Rosa?
You know, I go to conferences sometimes with these geek modelers, they'd hate for me to say that, but physicists who study the properties of fog and look at what are the condensation nuclei for fog, how much is sticking to what size of a particle, where's it coming from, how fast is it being pulled inland by what amount of heat in the desert. And I go up to them and say, I'm a botanist. Is it going to be more foggy or less foggy on the islands? And the answer I get is, you know, we're not really sure. What they're sure of is that it's changing and it's going to change, and we've measured that it is changing. But there's one school of thought that says as climate gets warmer, which it's predicted to do and is doing right now in Southern California, that's going to drive an even bigger uplift in the desert, and it's going to suck even more water in from the ocean. So it could get foggier, which is kind of a weird thought, you know. It's warmer, hotter, and drier, and foggier at the same time, but that could happen. The other thought is the system is going to be in some sort of disarray, and the fog may be pulled inland, but it may not be in the same patterns that it's being pulled inland now because of other changes at sea that have to do with the warming of the ocean temperatures as well. So there are models that make our little one-page model look sort of pathetic, that, you know, people are measuring this stuff, and the jury's still out. But I think what's clear is that it is changing on the islands, and we need to be cognizant of that when we decide where to put our restoration. And that's why for this near-term project, we're looking really at the most inundated places because they're the least likely to change. Yeah, good question. Yeah, there's one back here.
Talking about that, is there a plan for the other islands, restoration plan coming for the other islands?
Right now, the restoration plan is pretty much passive restoration post-animal removal. The park is doing a lot of monitoring to see where are things recovering and where not. Where do we need to put restoration on the landscape? But this stuff is expensive to do, and so we're doing it in a kind of a microcosm on Santa Rosa to see if we can develop techniques that we can export to other islands. Now, having said that, there are a lot of focused efforts, like Ken Owen's group, who is really working hard on getting rid of invasive weeds. That's a restoration project that's been going on for years. Other projects that look at restoring habitat for particular species like shrikes or foxes. So there are focused projects looking at the needs of particular organisms, and I'm actually starting a project focused on the restoration of some rare plants. But this is our first overarching kind of ecosystem-wide effort at a restoration that we hope will percolate through the system from the ridges down to the valleys. Yeah, one more?
I noticed some little screen things out on Anacapa Island next to the seedlings. Are those collecting fog?
I'm glad you mentioned that. That is a restoration project that has been going on and very successfully. That's a project that's, I think, in its third year or fourth year right now. That's spearheaded by Sarah Cheney with funding from the Park Service. The project there was to get rid of ice plant that has been covering the island, planted there for erosion control by the U.S. Coast Guard, and replace it with natives. And what was happening was she was planting natives and the gulls were bothering them, and so she actually said, I got to pick these little cones over the plants to keep the gulls from sitting on them. Ken was working with her, and you probably could wax more eloquently about it, but those cones and those screens had the effect of not only protecting the plants from gulls, but also watering the plants, and it worked great. And so we're using that experience on the island as part of our toolkit for Santa Rosa as well. Well, it's 8 o'clock. You all have been here for an hour or so. I appreciate your attention. You may have seen as you came in, there was a slideshow kind of running in the background here. I've asked a lot of friends and colleagues to send me pictures of fog, trying to convince them that it's actually beautiful also, and actually you can photograph it. And so it's a collection of photos that people have taken and sent me, and if you have any pictures of fog that you'd like to send, here's my email. I'll put your name on it and stick it in our photo collection. Thanks.